We're going to talk about trigonometric functions of any angle. Example 1. Find the exact value of each of the 6 trig functions of theta if -6, -7 is a point on the terminal side of the angle theta. So let's draw a little picture here. So we have coordinate axes. I plotted -6, -7 in the third quadrant. So next, I'm drawing a triangle in that third quadrant. So from that point, -6, -7, shoot straight up to the horizontal axis to make a right angle, and then also take that point and connect with the origin. And there's my angle theta from the positive horizontal axis here to the hypotenuse, which is the terminal side of that angle theta. So next I'm going to label the sides of my triangle ABC, C being the hypotenuse. So given my angle up here, I have A being the adjacent side, which is -6, because that's the x-coordinate of my point. The opposite side is B, which is -7, the y-coordinate of my point. And the hypotenuse is C. That's what we need to find to be able to use this triangle and find those trig functions. So using Pythagorean theorem, we have the 2 lengths of the legs of the triangle A and B. Square them. That's going to be my hypotenuse squared. So 36 and 49 add up to 85. Take the square root of both sides. We get root 85. So remember, the length of the hypotenuse is always a positive number. All right, so next, I'm going to use that triangle to evaluate sine of theta. So remember, right triangle trigonometry, sine of theta is defined to be opposite over hypotenuse. We found the opposite side, we were given the opposite side, right, -7, and we found the hypotenuse, which is on the bottom, root 85. Now we need to rationalize the denominator by multiplying top and bottom by radical 85. So when I do that, I end up getting -7 radical 85 over 85. So that's my sine of theta. Next, let's find cosine of theta. So remember, cosine is defined to be adjacent over hypotenuse. So I end up with -6 over radical 85. Similarly, I need to rationalize the denominator, and I get -6 radical 85 over 85. Next, let's find tangent. So remember, tangent is defined to be opposite over adjacent. And this one's pretty straightforward. We have -7 over -6, which simplifies down to 7/6. Next, let's find the reciprocal trig functions. So remember, the reciprocal trig function of sine of theta is cosecant of theta. So all we need to do is look at sine of theta, and what I want to do is use this right here. I want to use the non-rationalized version of sine of theta. The reason why is because we know we're going to have to take the reciprocal. So when I take the reciprocal, that radical 85 ends up on top, and then I'm done. Now you're more than welcome to use this version, but when you take the reciprocal, you'll end up with a radical 85 on the bottom again. Then you have to rationalize, and it's a bit of a mess. So always use the non-rationalized version, take the reciprocal, and then you're done. So similarly, we can find the reciprocal of cosine, which is secant of theta. So use that non-rationalized version, take the reciprocal, boom, -root 85 over 6. And then we have cotangent. That's the easiest one yet. Take the reciprocal of tangent, we get 6/7. Let's start example 2. It's very similar. We want to find exact values of trig functions, but this time we're given one. We're given that cosine of theta is -7 over 27. So we need to find 5 trig functions. Now we're also given that tangent of theta is less than 0. Now that will enable us to answer the question, what quadrant is theta in? So using the fact that cosine of theta and tangent of theta are both negative, I'm going to draw some little circles here and write in some information. Okay, so cosine of theta is negative in quadrants 2 and 3. And then we also know that tangent of theta is negative in quadrants 2 and 4. Now the only way to get both criteria to be true is if theta lives in quadrant 2. So here's a nice circle where my theta is right there. Now I've chosen to draw my segment here, my terminal side, pretty close to the vertical axis. And that's because cosine of theta is a pretty small number, 7 over 27, negative 7 over 27. So I know that horizontal distance is quite small in comparison with what the vertical distance will be, which is sine of theta. Okay, so in the second quadrant, it's definitely good to note that sine of theta is a positive value. So that will tell me later on when I find sine of theta, remember I'll probably have to take a square root to be able to find it, then I'll know that it's going to be the positive rather than the negative. Okay, so we have two different methods that we can use to figure out what sine of theta is. First off, we can use the Pythagorean identity. So we plug in what we have, negative 7 over 27 for cosine of theta. So square that out, 49 over 729. And it's a positive. Remember that negative's on the inside there, so it squares out, becomes a positive. I need to subtract that value from both sides. So let's get a common denominator, right? So we have to get a common denominator between 1 and 49 over 729. When we subtract those numerators, we end up with 680. Now next, I would have to take the square root of both sides to get sine of theta. So when I take the root, it's a positive. Remember, we discovered that sine of theta has to be a positive value. Okay? I want to take the square root of the top and bottom separately. That will enable me to simplify. So we know that the square root of 729 is 27. That's how we got it in the first place. Now, if you don't remember how to extract numbers out of square roots, check this out. So radical 680, right, which is on top here, okay? Radical 680, I can write 680 as 4 times 170. Now, if you take the square root of each of those two pieces separately, you can then take the square root of 4 to get 2. So that's how we simplified radical 680 to be 2 times radical 170. Okay, so remember there's two different ways to do this. So I've shown you how to use a Pythagorean identity. Now we can also draw a triangle to figure out what cosine of theta is equal to. All right, so remember that cosine of theta is defined to be adjacent over hypotenuse. So here's my triangle. Imagine that being drawn in the second quadrant, okay? So we have the hypotenuse is 27. That has to be the positive value. And we have the adjacent side as being negative 7. So what we need to do is find the opposite side, which is b. I just picked b at random. All right, Pythagorean theorem. Plug those values in. Negative 7 squared plus b squared, 27 squared. Okay, so square those values out. Subtract 49 from both sides. We get 680. So take the square root. We get b is root 680, which, as we saw before, simplifies to 2 radical 170. So we're getting the same values, which is a good thing. If we didn't, something went wrong, right? Okay, so then we can conclude that the sine of theta will be opposite over hypotenuse, which we found opposite to be 2 radical 170 over 27. There you go. So we get exactly the same answer, two different methods. All right, so now that we have cosine and sine, we can figure out the rest of the trig functions, 4 of them, right? So we have tangent, cotangent, secant, cosecant. So again, 2 different ways we can do this, 2 different methods. First, we can use the fact that, starting with secant theta, that secant theta is defined to be 1 over cosine of theta. So take the value that we have, 1 divided by negative 7 over 27, multiply by its reciprocal to get negative 27 over 7. So an alternate way of doing this is to use right triangle trigonometry. So from right triangle trigonometry, we know that secant of theta is defined to be hypotenuse over adjacent. So we plug those values in from what we have, and we also get the same answer, negative 27 over 7. So next, cosecant. Now this one's a little bit more complicated only because we have to rationalize a denominator. Okay, so cosecant of theta is defined to be 1 over sine of theta. So plug that value in, multiply by the reciprocal to get 7 over 2 radical 70 right here. So this is the point where we need to rationalize. So if we multiply top and bottom by radical 170, that's how we get this radical 170 on top. And then we get a 70 on the bottom because we took radical 170 times radical 170. So the last step is just to multiply the 2 through to get 340 in the denominator. So similarly, cosecant of theta, using right triangle trigonometry, is defined to be hypotenuse over opposite. So plug those values in, 27 over 2 root 70, which is exactly what we got over here. Look at that. And so I make that jump and rationalize to get the same thing, 27 radical 170 over 340. Next, tangent of theta. So remember, tangent of theta always defined to be sine of theta over cosine of theta. Plug those values in. Be sure and multiply by the reciprocal of the denominator. Now I can simplify out the 27 and I end up with a negative 2 radical 170 over 7. And that should make sense, it's a negative, because remember, theta lives in the second quadrant. Tangent's always positive in the second quadrant. All right, good. So alternate way of doing it, which looks a little bit easier actually, is tangent of theta is defined to be opposite over adjacent. Plug those straight in and we're done. All right, so that one was a little bit easier. Okay, so next, cotangent, the last one, cotangent of theta. So cotangent of theta is defined to be cosine of theta over sine of theta, which is the reciprocal of tangent, right? So plug those values in, negative 7 over 2 radical 170. So just like I've done before, multiply top and bottom by radical 170, simplify by multiplying the 2 times the 170 in the denominator, and then we get our answer, negative 7 radical 170 over 340. All right, so this one takes about the same amount of work. Using right triangle trigonometry, cotangent of theta is defined to be adjacent over hypotenuse, or I'm sorry, adjacent over opposite. So we plug those in. If we rationalize, we get exactly the same answer. So in trigonometry, just remember that sometimes there's more than one method. So for example, here we have using the reciprocal identities. For example, cosine is 1 over secant, or alternatively, secant is 1 over cosine, or we can use triangles with right triangle trigonometry.